packing efficiency, okay, refers to the volume of the spheres divided by the volume of the unit cell. If you were to assume, okay, that each particle is a sphere of the maximum possible size that could fit in a cell, okay? So you assume you have a unit cell. Imagine you have the maximum possible size spheres that you can fit in that unit cell, and they're all equal size. What we call the packing efficiency is the amount of space that's occupied by these spheres divided by the actual volume of your unit cell. Okay? So, and you'll find that for a simple cubic cell, the packing efficiency is 52.3%. Why is that? Here's how we can figure that out. Imagine you have a cubic cell right here. You're looking at it from the top, right? So it's packed with spheres and as big as possible. So if the spheres are as big as possible, what happens? The radius of your sphere, of this sphere, plus the radius of the neighboring sphere together, 2r, that's going to be equal to the side of the cube, correct? So the length of the side of the cube is 2r. What would be your volume of the cube? It's going to be a cubed, right? And which is going to be equal to what? 2r cubed, correct? What would be the volume of a sphere? You remember the formula for the volume of a sphere? It's 4/3 pi r cubed. Okay, so that's the volume of one sphere. Why are we talking just one sphere? Effectively, what did we say? How many did we say? How many spheres would be in your simple cubic cell? It's just one atom, right? One sphere. So that's the volume of the sphere divided by the volume of the cube. What would that be? So volume of the sphere is 4/3 pi r cubed divided by the volume of the cube, which is a cubed, which is 2r cubed. That's your packing efficiency. And so what would that be? Your r cubed cancels out, right? So this is going to be 4/3 pi in the numerator divided by, okay, you got your r cubed there. And 2r cubed is 8r cubed. Okay, so r cubed cancels out. And that gives you 4/3 pi over 8. So let's simplify this. That's 1 and that's 2, right? So and that's pi over 6. Correct? So what's pi over 6? Pi, where is pi over here? Let's just do 3.1416 divided by 6. It's 0.50, it's 50.524, okay? Oh, here's pi. Pi divided by 6 is 52.4, 0.524. Okay, so it's 52.4%. Make that correction. So this is going to be equal to 0.524. So you're looking at 52.4%. Right? So that's what you call the packing efficiency. What about if you're dealing with, okay, here's an example. Polonium. Okay, going back to polonium, what's the length of one side? We said was 335.9 picometers. Okay, let's figure out what's the size of a polonium atom is. Right, based on this information. If it's a cubic cell, okay, here's one polonium atom, here's the other polonium atom, simple cubic. And this is the radius, right? And that's the radius. This is center to center, right? So A, the side of the cube, we say is equal to 2r. So what's the radius of a polonium atom then? If you were to imagine that as the side, that's one way you can determine the size of atoms, okay? Based on crystal information. So what's the radius of your polonium atom? It's just going to be A over 2r, A over 2. What's our A? 335.9 picometers divided by 2, which gives us 167.95 picometers. So it's about 168.0 picometers if you do your sig figs, right? That's the radius of your polonium atom. What is the what is the volume of your polonium atom? How much volume does it occupy? Four thirds pi r cubed. So 4/3 times pi times 168.0 times 10 to the negative 12 meters cubed. Okay? What's the packing efficiency? Actually, we don't have to calculate packing efficiency. We should already know what it is, right? It's 52.3%, right? 52.4%. Okay. And so if you did calculate your volume, you'll find it's 1.984 times 10 to the negative 29 cubic meters.